Okay, I'll continue with some properties of Bloch functions and Bloch theorem. Maybe I'll spend another week on that to show more details. And then I'll start showing some applications. So first I want to start with how do we define metals versus insulators. And what's that?
What about semi-metals?
And also semi-metals. Also semi-metals. I don't know. There are other like semiconductors, whatever, and all others. Let me say, all others. It all comes from band theory. And so let me first write the Bloch theorem. So this is Bloch theorem. There were like, we derived different versions of Bloch theorem, but one we used, one of these was psi k of psi k of x plus a was equal to e to the I k a psi of x, also k. But we also said this is coming from the commutation of like, or this is coming from the translation operator, but also we impose additional periodic boundary conditions, and it was like psi k of x plus n. Maybe I can write it like L, and L was n times a, was also psi k of x, right? And from here, combining these two, we found something like this: e to the I k n cell times a is 1, and from here k was equal to 2 pi over a m over n cell, and m was going from minus n over 2 to n over 2 minus 1. So here in total there are like n, let me call it states. There are n points in a K space. So we can see exactly the same thing in another way. Okay, another way, maybe another way to exercise your earlier knowledge. Another way. So n states. I think most people here know how to find density states, right? I think if not, you can ask and we can show, but it is something like this. You sum over all k points, the unique k points, which is in the first Brillouin zone, and each k point is going to come with 2 pi over L states. And if you integrate, you are going to find the total number of states, and total number of states is L over 2 pi over A. Cancel that with this. This N is N cell times A. Cancel this A with this, and you have NC. So this means number of states is equal to number of cells. So this is another way, the one state per cell, but this is for like one band, right? We can have multiple bands per band, but we also have like Pauli, right? We have nothing about spin so far. We can also incorporate spin, and this is going to be per spin. And let's draw like a cartoon band and see what this means. So this is, for example, let's say the first band. So this is minus pi over a to pi over a. Maybe there is like a second band here, and so on. And we draw this continuous line, but in reality, this is not the continuous line, right? Continuous line exists in our imagination. Real life doesn't work like that. There's like a point here, another point here, another point here, another point, and so on. These are all K points. In total, we have n cell K points. And now the second question to determine if this is going to be like a metal or insulator is how many electrons do I have, right? So right now we only found something geometrical, if you want. Like there's only a single electron, and this gave us the available states. Now we have to occupy these states with the electrons we have, and for that you have to tell me how many electrons does a given system have. We can, for example, consider so-called, let me write it and explain, odd valence Bravais cells. What this means is like each Bravais cell is going to contribute 1 electron or maybe 3 electron or like 5 electron, odd. And odd means what? Like odd is you have like 2n plus 1 electrons, and you can first try to occupy these 2n electrons, right? So each cell contributes, let's say n is equal to 1, because the calculation is the same for 5 and 7 and so on. So each K point I can put 2 electrons, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, right? And then at the end of occupying whole band, I go to the second one, right? Now suppose there's like a band at the bottom, I occupy it completely, and I located these, I found rooms for these electrons. Now I have this additional 1 electron per cell, but for 1 electron per cell, I'm going to fill only the half of this band. It's going to be like this, right? This is what we call half filled. And suppose you are like an electron here. You are like an electron here, right? And I give electric field. For all intents and purposes, electric fields in almost any solid state system is weak, tiny, right? And tiny means it's going to be a small perturbation to lift this guy from here to here. And that's all you need to observe current. And if you are able to do that, right, if there is like an empty available state here, right, so this electron is occupied, and below, like, so this is what we call Fermi level. So this is occupied, and below Fermi level, and I get with like arbitrarily small energy coming from electric field, I can excite it to an empty state here. So this is empty, and this is going to give us conduction. On the other hand, if we had one more electron, right? So this band is half filled, and one more electron per cell is going to fill the other half. And in this case, Fermi level is going to be somewhere here. And suppose you are this electron, I think you can, like all the other electrons that already require more energy, and you want to like get some energy from the electric field and contribute to conduction, but there is no state here, right? It is so that is gapped. So this is gapped, and this is going to be insulator, right? So this is insulator, and this red one is going to be metal. So that's why, like odd valence Bravais cells, this is like alkali metals, fine metals. Like the name suggests, they are metals. They have generally a Bravais lattice structure, and they have 1 electron contributing because the valence of each atom is 1, and they are going to be metal. On the other hand, like there are some even valence atoms like silicon, germanium, carbon. Even though, like, so as we mentioned in the previous lectures, these are like non-Bravais, but still this argument like with some corrections works, and these are insulators. But like all rules, there are like notable exceptions to these rules, and sometimes bands overlap, right? And an example is, okay, exception is, I think this is zinc, right? Is that, let me not mistake. So it may have like a band like this, like one side is a little higher than other, and you have another band. Okay, let me exaggerate another band like this, and the Fermi level could be something like this. Here, right? You occupy all the levels below. In that case, like there is like a band overlap, right? When there is like a band overlap, you can have like so-called Unquam processes, right? You can have like a momentum changing excitation, because they're like exactly like energy reservoir coming from energy. There is also like moment. What is the source of momentum in a crystal lattice?
Vibrations.
What's that?
Vibrations.
Exactly. There is like a gigantic pool of phonons, and they can provide any momentum you want, and they can give conduction. Another exception is also, I think we are not going to talk about this, but this is like a kind of like a research area. This is like electron-electron interaction also modifies this picture. In this case, for example, even at half filling, you can have an insulator, like even a band like this can be insulated due to electron-electron interactions, and we call them Mott insulators. But typically, we are going to have this picture in our mind, like odd valence Bravais cells are metals, and even valence Bravais cells are insulators, as like a starting point. So the second thing I want to talk is like something called one Hove points or singularities. And the band is like, we can do like the reduced zone scheme, or we can do the extended zone scheme, but sometimes we can also do repeated zone scheme. And the repeated zone scheme, so this is the energy. If you want, this is E of k. So this is, let me write it a little bit bigger. So this is k. And so there is like a Brillouin zone. Okay, here is the Brillouin zone. Let me make it a little smaller. Here's the Brillouin zone, and the band is something like this. But outside the Brillouin zone, we can just repeat it in the repeated zone scheme, right? It's going to be something like this. Actually, let me copy. Okay, this one works. This one works. And similarly for the excited state, or like second band, I have like something like this, and I can repeat it outside. And what you can see here is like there are like points, right? The question is, what is the number of states at a given energy? So this is the energy direction. This is the k direction, and in the regions where this is flat, for example, this and this and this and this, you can see there are like even if you change k point, energy does not change, right? Even if you like, it is like kind of like flat here and flat here, even if you shift k a little bit, you are still at the same energy. That means there are more states at a given energy. And we can like see this more systematically. Like let's consider energy density of states, and this is given by rho n of epsilon at a given epsilon. So this is epsilon without any index is the energy I'm interested in. And to find the number of states, I'm going to integrate over all Brillouin zone points. Let's do it in D cube. We can do it in 1D and 2D. And there's like L, but this is energy density of states per volume. So this L went to here to give us something per volume. This is cube. And to find the energy density of states, I have put this epsilon minus epsilon n of k. So this is the band. So what we can do is like we can do this integral not from the Brillouin zone but equal energy surface. E is equal to E and k and d cube over 2 pi cube. Now we can like try to change the integral variable. So here's the volume in k space, something like that. And this is, if you want, my k. So this is I'll call dsk, the area element, and this length here is dk, the width of this shell. And I'm going to write this d cube as d cube k is equal to the width dk times ds, and I'm going to divide by d epsilon n of k multiply by let me write it like that, d epsilon n of k, and this one I'm going to write it like there's no integral yet, so d epsilon n of k ds, so there's like a k here, k divided by, so this is like a derivative, but in the three-dimensional case, right, there's like a directional dependence. So to take care of this, I'm going to write it like a gradient. So I take this dk over de and write it like de over dk in the denominator and generalize it into 3D by making derivative the gradient en of k, and I take the absolute value. So this is the generalization of this intuitive derivation. Then what we see is rho n of epsilon is going to be this equal energy surface, Enk is equal to epsilon 1 over 2 pi cube dsk divided by gradient k of epsilon of k. Therefore, we can see when gradient epsilon of k diverge, we have a large density of states, and it's something like this. Suppose this is the k, this is energy, and there is some, for example, this happens at the Brillouin zone boundary, right here, right, and here, but it happens in the more, like this is like a one-dimensional picture. In 2 and 3 dimensions, this is generally happening in the Brillouin zone boundary. What happens is like this is not E, but this is rho n of E. There will be a divergence of density of states, and it's going to come back. And this one is what we call one Hove singularity.
So can I just roll up that? I missed the part from derivative part from the d cube k resulting expression into the integral part.
Yes.
Can you explain that part?
So what I did, like my starting point is, so this one, and I say let me take d cube k, but the volume element, how do you write volume element? This is like dx dy dz if you want, but I can like write it like some surface times the thickness of that surface. So this is what I do, and then in the second step I like, of course this is like because we are physicists, we can do these stupid things. I divide by d epsilon and multiply by d epsilon, and then this object I write it like 1 over d epsilon dk. And then later I say, okay, this is like three-dimensional, there is like a directional dependence. The correct thing to do is write it as a gradient, not like a one-dimensional. And after that I have this.
I mean, I'm not asking for the integral. I mean, how did you form the final integral?
So this integral?
Yeah.
So now from here to here, what did we have? This integral said, okay, sum over all k's in which epsilon is equal to epsilon of nk. This is saying that take the equal energy surfaces in the integral. And here I wrote it like, I wrote exactly the same thing, but I wrote it as a boundary condition in the integral. So this is rewrite, but the rewrite shows us the role of the gradient of epsilon. Maybe I can give you an example real quick and then continue. I think I have. So we can model solids. Like typically we have like a Schrödinger equation and a periodic potential, but in real life things are not solvable, right? We have to model things, and a very common model is going to be like a tight binding model. In a little bit, I'll show you details. But at the end, we are going to have bands like this. For example, Ek in 1D is going to be minus 2t cosine Ka, or Ek in 2D is going to be something like this, minus 2t cosine Kxa plus cosine Kya. At the moment, you don't have to worry about this. Like we can say that, like, okay, this is given to us. Let's see how this one Hove singularity looks like. And to do that, it is actually very simple. Let me take this as a phenomenological constant, some t. We are going to have a lot of talk about these things later. And this is the A lattice spacing. Let's take this, and I have some k's. You can read, right? Okay, so this is range minus pi over a to pi over a, and let me not take too many points. Let me take 0.01, and what I want to do is, like, I want to see how many states do I have, right? How do we, like, the energy is like something like this. Let me call it epsilon k is equal to minus 2 t cosine k's, and let me see if it works. Okay, it seems to be working. And now the question is, how do I see the statistics of like these energies? What is the comment? You histogram it, right? Like you just divide the energy into bins, and you epsilon of k. Let me see if that works. It worked here. Oh, I think yes, you are right. So this, right? That's what you said. I see. Now I need to uncomment this. Okay, something like that. Let me increase this to 40 points and put some ticks for you to see where they are. Ticks. Minus 1.9, minus 2, and the second ticks, I don't care. Something like that. And here, this band is, so this, the first one, the first example. This is like a simple cosine. Let me pull this aside. It's like something like that. Right, and the cosine, the boundaries are minus pi over a to pi over a, and the minimum energy, if you put k is equal to 0, it's going to be minus 2t, and maximum energy is if you put k is equal to pi, right? This is minus 1, minus is plus, this is 2t, and since we took t is equal to 1, it's going to be minus, it's going to be going from minus 2 to plus 2, but because they're like numerics, they don't put ticks to where you want, so you have singularities at this point, and minus 2, this point. Right? This is exactly what we are seeing. So let's also do exactly the same thing in 2D. First, let me draw the band for you, how it looks. Because this band is kind of like a very typical for us, minus 2t cosine. Let me not write like kx minus 2t cosine ky, and I want to take kx to be minus pi to pi, and ky to be minus pi to pi. Oops. Let's see. Okay, so this is the band. If you like, there's like two cosines. It's kind of like a ball, but as soon as you converge to like zone boundaries, you form this perfect square, right? And then there are like hills here, like hills on the corner, and there's like a ball in the middle. So I think I change this a little bit. Now I want to see the density of states for this thing. And how did I do this? Okay, let me do, I need to form a table. Actually, let me do this to convert this to a table. And kx here, comma k's, and ky, comma k's. And let's see if this works. Yes, it works. But I need to flatten this. And the way you do flatten is, let me do here. Because it is going to be like a nested, and each component is going to be histogrammed separately. I think this works. Now I can do the histogram. It's like a terrible way to do this, but I think it's going to work. Okay, here you can see when you go to this zero energy, right? This like zero energy, which happens to be the Brillouin zone boundaries here and here and here. But also you can see there's like a zero energy. There's like a large portion. You have like a blow up in the middle, and then it decays. It's like compare this with 1D, right? As an exercise, you can also consider, okay, exercise, show this in 3D. You just add one more cosine with kz, and let's see what it looks like. Okay, there is now like one more calculation. Let me try to see if I can finish this. If not, maybe I can take 10 more minutes from your break. So I want to calculate velocity of these Bloch electrons. Let's calculate the velocity. And if you remember, our job is to solve Schrödinger equation, h psi is equal to e psi, and h is equal to p squared over 2m plus v of x. V of x is equal to v of x plus a, and the wave function is going to have this form, e to the I kx u k of x, and I leave the band index implicit because there will be no band mixing in this calculation. And here the condition for uk is uk of x should be equal to uk of x plus a. Now I want to hit on this wave function with momentum. P times psi k of x is p times e to the I kx u k of x, and p is minus I h bar del del x. And when I now use the chain rule, I can hit with the derivative here or here. If I hit here, it's going to be h bar k, and I want to write this on the, like, I want to write it e ikx h bar k u k of x plus e to the I kx. Now the part acting on u, I'm going to write it like p. I'm not going to take the derivative anyways, right? Now I combine this, e to the I kx p plus h bar k u k of x. So what this tells us, p acting on something like e to the I kx times something else, like jumps over e to the I kx, generates a p plus h bar k factor and the other one.
So p is the operator, isn't it?
Yes, it is the operator at this moment, yes.
In the first term, you took the derivative of the exponential, right?
Yes.
So there should be an I.
There should be, but there's like I, but there's I here, right?
Ah, okay.
They canceled, that's why I got h bar k. And in the second one, I just put it in back to like p form. If you want, this is, at some point, when you do quantum mechanics, you stop writing heads because you know what it is. But if you still use that practice, put heads to remind yourself. Now I want to do this one more time. P squared psi k of x is going to be p times this entire thing, right? One of the p's I already took care. And I also know, like, this is now like something like e to the I kx and something else. But now from this calculation, I already know how p behaves, right? P behaves in such a way, it's going to jump over e to the I kx. It's going to generate a p plus h bar k factor, and it's going to put whatever next in an unchanged form, like this. But these two are exactly the same, so we can just put a square and delete this. Good. Now we can write the Schrödinger equation. This Schrödinger equation is going to be h psi is equal to e psi. One factor is this. So this is p squared over 2m p's, p squared over 2m plus e to the I kx v of x u k of x is equal to e to the I kx e of k. I leave the band index implicit, u k of x. Now this e to the I k x did its job, and we say thank you, and we just delete. And what remains is, okay, let me just copy, not write the whole thing again. So this one is gone. This one is gone. So, and since this u is periodic, this is a Schrödinger equation that needs to be solved only in the unit cell. So it needs solution in unit cell, which is like a drastic simplification, right? There's like entire solid. You don't have to do that. By doing this transformation, you only solve in the unit cell and you're done. And you can treat this unit cell kind of like a particle in a box, right? And we know how to solve particle in a box. So so this was the first thing towards calculating the velocity of Bloch electrons. Now there's like a second piece we are going to use, and this is what is so-called Hellman-Feynman theorem. Actually, I think I can prove it real quick. Let's try to prove it. Like, suppose you have like a Hamiltonian that depends on some parameter, and you have some states. Of course, states also depend on this parameter, and there's like some energy E lambda. This also depends on parameter. In a little bit, I'm going to leave this parameter implicit, but you know, like from here, everything depends on parameter anyways. Now I want to take the derivative of this entire equation with respect to lambda. So del lambda h, and so this is the first derivative. H, the second derivative, I will write it like this. Del lambda n is going to be equal to, And I do the same thing on the right hand side. Del lambda E n plus E del lambda n, right? I leave all lambda depends implicit because it's going to be really crowded otherwise. Now I'm going to take multiplication with bra, the entire thing. And this is going to be n del lambda h n plus n h del lambda n is equal to, so this is just a number, right? This n is just going to commit with the number, and you are just going to have this del lambda e, and we are saying this, these are normalized. And the second piece, okay, this one is also like a number, it will commute, and this is going to be e times n del lambda n. And now I look at this object. So Hamiltonian is like a Hermitian object. I can act it on this side, I can act it on the other side. I can act any way I want. For this one, I choose to act it on here, and it's going to give me the energy. So this is going to be then getting outside this bra and ket, and E times n del lambda n, E times n del lambda n, and this guy is going to cancel this one. At the end, you have del lambda E is equal to n del lambda h n. So this is Hellman-Feynman theorem. Okay, I'm almost done. We can apply this theorem to Bloch electrons. And so del, let me write it in 1D. You can do it in any dimension. You just need to convert this derivative to gradients. And for some energy now, let me write band index is going to be equal to, right? And here, like this equation, I am thinking about this equation like this: H, U, and K is equal to E epsilon n K, U, and K. And I'm going to apply the Hellman-Feynman to this form. And this is going to be equal to U and K del H. Of course, here this H also depends on K, because there's K here in the momentum. So this is del HK, del K, U, and K. And I want to put like a factor of h bar here, 1 over h bar, 1 over h bar. Now I can take the derivative, right? So h, let me write it here. H of k is equal to p plus h bar k squared over 2m plus v of x. And the only k dependence is here. Let's take the derivative. Del hk del k is going to be equal to 2 will come in front. It's going to be p plus h bar k over m. But there's like one more h bar, so this is h bar, so that's the derivative. And this h bar is going to cancel this h bar. Then this equation is going to be u and k, p plus h bar k divided by m, u and k. Good. Now I do what I did in backwards. So here I want to put a factor of e to the minus I kx, e to the I kx. Here I put a factor of e to the, I think it doesn't matter what, e to the I kx, e to the I kx. And now I know how this p operates, right? Any function of p is going to behave exactly the same. But okay, let me write, not to confuse anyone here. So this p plus h bar k acting on e to the minus I kx, e to the I kx, u and k. So I divided like piece number 1, piece number 2, and the way it's going to act is going to be jump over piece number 1, it determines I kx, and put wherever you see p shifted by k, but now this there comes with a minus, so right, p minus h bar k, and now I'm writing the second piece, h bar k, and write the second piece. And the second piece we are not going to operate. So this one is going to cancel this one, and this one we are going to call it full psi k, psi nk if you want. Is that clear? And that's the end of the calculation almost. Then 1 over h bar del k epsilon of k is equal to, so let me write this thing. So this thing, I have this thing, now I have this thing, and I have, let me write it like this, and I think I forgot to write p in the middle, and I have of course p, and there is 1 over m here. So this one is going to cancel this one, and this piece is going to be a bra form of psi n of k. Then at the end I have psi nk, p over m, psi nk, and what is the expectation value of p over m by definition? That's the definition of velocity, v n of k. Then we found that, let me now generalize it to an arbitrary dimension, v, which is going to be a function, it's going to depend on band and the Bloch momentum. It's going to be 1 over h bar gradient E n of k. Okay. Let me say one more thing and let's take a break. And what does this tell us? Let's draw this cartoon bend one last time before the break. And I have something like this. And here's pi over a. Here is pi over a. So this is epsilon of k. This is k. Here, what is the velocity based on this? V is 0, right? In this region, what is the velocity sign? Right? This is v less than 0. Here, v is again 0. Here, v is positive, and here, v is again 0. So what this says is, like, as you go along the band, you first stop, you go in the minus direction, right? Negative velocity, and then you stop, and you go in the positive direction, and then you stop. And that means what is the particle doing? It's just oscillating back and forth. And these are so-called Bloch oscillations. And so this is like a theory, and like people knew about this, like, I don't know, 50, 70 years. But in practice, this is never, this never happens in real solids. Why? Huh? Yes, there are some perturbations, but what kind of perturbations? The perturbations that break translational symmetry, right? Like impurities, phonons, anything. They are going to, like, what we say is, like, as the electron executes this Bloch oscillations, some kind of perturbation breaks the coherence, and as a result, you forget your memory and you never see this full period. But there are some systems, like really like clean, very low temperature fabricated systems, or like engineered artificial systems, like cold atomic systems. They can observe low oscillations, but it is generally not seen. So it's something you don't have to worry about. Okay, any questions? Let's take a break and continue in the second hour.